Okay, so tonight I want to talk about Ito's lemma, famous lemma about Brownian motions and using a function that is described by a Brownian motion to create another statement about that function. So I'll be going over Ito processes and also geometric Brownian motions to start off with. Okay. So, by definition, a geometric Brownian motion is basically, this is one where we're not going instantly, we're not taking time instantly, but the change in a variable, and we'll use S because eventually this will become a stock price. The change in the stock price divided by the stock price ends up being, we'll use this Greek letter, multiply that by the change in time, so this will map to being our interest rate. So we'll take that amount, and then we'll take sigma, which is going to eventually map to our standard deviation, multiplied by an epsilon, which is a standard normal. So that would be a normally distributed random variable with a mean of 0 and a standard deviation of 1. And then multiplying that by the square root of the amount of time we let go through. Then multiplying both sides by S, we get this formula. So it's really two different ways of saying the same formula. So again, the delta S is the change in the stock price, or whatever S is. Mu ends up being the expected rate of return. So the more time you give it, this is how much it goes up by. And again, this is a discrete case, so this is not a continuous case. Sigma is the volatility of the stock, which will map to a standard deviation. And then the sigma times the epsilon times square root of delta t is the stochastic component, and its variance is this part, this component squared, without the normal part taken out. So this ends up being the variance because that's the standard deviation squared. The stochastic component of it is the part that we can't use standard calculus on. We can't use the Riemann sum model for integrating. Okay. So we needed a type of calculus for this type of mathematics, and then a famous mathematician, a Japanese mathematician by the name of Ito, he passed away a few years ago, but he came up with a lemma about processes like this. So we'll talk about what an Ito process is, and then if you have an Ito process, we'll apply this lemma to it to give us another Ito process. And that other Ito process will provide us some interesting information. So an Ito process can be generalized as a Wiener process in which the parameters A and B are functions. So they don't necessarily have to be constants, but we'll be doing examples where they're constants and some where they'll be functions. So A and B can be a function, and then we're going to model A will end up representing some type of rate of growth, and B will end up representing a magnitude that we're going to multiply the Wiener process from. So you may have seen this as a Z in your other textbook, the DZ here. Okay, so some textbooks you'll see this as a B for Brownian motion. Sometimes you'll see it as a W, and sometimes you'll see it as a Z. I don't know where the Z comes from. But, okay, and this is where the W component is an m-dimensional standard Brownian motion, and the A and the B end up being n-dimensional. So this formula applies for where we could have many stocks. It doesn't have to just be one stock. We could have a collection of independent stocks, and this whole formula would apply to it. Okay, so basically we're saying the current price of a stock at any point in time is equal to what it started off at times 0. We're going to integrate from 0 up to a point t, add up all the interest we gain. So this will end up being just the pure gain of interest. And then this will be the randomness of the stock. This will be some magnitude times a Wiener process, and then we just add that up over time. Add the whole thing together, and that will give us a model for what the stock price will be at any particular point t in time. Okay? So then just continuing on, another way to write that integral we had before is write it as a differential equation. So basically this equation is the derivative of the previous formula. So instead of it being xt, we take the derivative of it, and then the integral part, we take away the integral sign, and we just get a of t dt, b of t dw. So this ends up being an n-dimensional stochastic differential equation, which has this form. So we end up, like I said before, we could use this, in the simple cases, this could just be a constant, and this could be a constant. Otherwise, the variable a, which is the component of growth, could be a function of the stock price and time. And it could, again, it could just be a constant if we wanted to. This can also, over time and over the price, change in the stock price could change too. So this is the more general case. And we now have a differential equation. And we also have an initial condition that the stock price originally started at some number. So in a concrete example, we might say, you know, IBM stock is currently at 100. How would you model where it could go into the future? So this ends up being a differential equation, but because there is a stochastic component of it, we can't use normal differential equations to solve this. If we then were to integrate this equation, we'd end up back with this differential equation. The one that we had before, actually. Probably should have put a subscript of 0 here. Okay. So now this component, since this is a function of just the stock price and time, we could use standard calculus to solve this component. This one we couldn't because this is being multiplied by a Wiener process, which we can't do standard integration on. Otherwise, we'd be able to just solve this differential equation using standard methods of solving a differential equation. Okay, so Ito's lemma, and we're not going to go over the proof of this. Ito's lemma basically says this. This is a very powerful statement. And when we go over some examples next, well, yeah, at the end of these slides and also next, we'll see an example of this. But it's basically saying this. Suppose you have something that follows an Ito process, meaning its rate of change equals some component times time, so it's growing at a rate, and then also has a variable part to it, a part with a, I'm using Z. So you can tell I copied this from 2 different textbooks. This Z is the same as the W from the last slide. So, and then this is a magnitude being multiplied on top of the Wiener process. Okay, this is where dz is a Wiener process and a and b are functions of x and t. If this is true, let's say you have some process that is modeled this way, then if you have another function, any function, you can actually make up any function g, which is of the variables x and t. So this would be like our stock price and this would be time. This statement in red is always true. The rate at which the g function changes is equal to the first derivative of g with respect to x times a, plus the first derivative of g with respect to t, plus 1/2 the second derivative of g with respect to x times b squared. You multiply this component, this whole thing gets multiplied by dt, and then also plus the first derivative of this function g that you've made up with respect to x times b gets multiplied by the same Wiener process. So what this is saying is if you could come up with any process that's modeled this way, if somewhere out in the real world there's a process that's modeled this way, and we could kind of argue that stock can be modeled this way. So yeah, let me just take a second to talk about this. Stock can be modeled in such a way that it's variable, it has a randomness, it could go up or down. Some stocks are more volatile than others, have a history of going up and down at a much higher rate than those, and that's why we use this here, to multiply how much variability there is to it. In addition to that, investors expect, on average, risk-neutral-minded investors expect to make money at least at the rate of interest. Otherwise, they just put the money in the bank and gain interest. Why would they buy stock? So there should be a component that, as you multiply it against time, there's expected growth. So we could make the argument that we can model stock with this stochastic differential equation. Now, some people might argue this doesn't perfectly model stock, so I just wanted to point this out. This component could, since we don't have any control over it, it's just a random process, this could get so big that it's bigger than this part. And then the price of the stock could theoretically go negative here. But in the real stock market, as the price of stock gets near zero, the company closes and it never goes negative. But in this model, we could actually go negative. So it's not a perfect model for stock, but yet we can use this to model stock. Now the question is, if this is the model for a piece of stock, you could turn around and say, well, I have a new function g, which is basically 2 times x. That's a really easy example. G equals 2 times x. Then the rate at which g changes ends up being this formula. So we have the freedom now to make up any function g, which takes as input x and t. This statement about the function g we've made up will always be true. And if you think about it, this is another Ito process, right? What is an Ito process? The rate of change equals something times dt plus something times dz. And that's what this forms into. So we could take any Ito process, make up any function we want, any function g we want, and this statement will be true, so the g function will also be an Ito process. And it's just a matter of calculating these first and second order derivatives and plugging in the formula. So this unfortunately ends up being a formula you have to memorize, because it's not easy to just off the top of your head remember it. It's not intuitive, so any test question, hopefully the teacher puts that on the test. So it's just a matter of finding out what the function is and then taking those components and putting the formula together. So an Ito with drift and variance basically is saying this. Like I said last time, the g function, which is any function we can make up but uses x as input, that will also be a Ito process. It has what we're now going to call a drift rate. So drift rate is basically, as time goes on, it's angling upward on average. So the first component, the big component in the middle, ends up being the drift. So let me just explain what I mean by that. So the Ito process has 2 components to it. The 2 components are what we're calling the A part, or this component, is basically making our process drift on an angle upward. I'm assuming this is positive. I guess we could have negative interest if we want, or in a non-financial sense, this could be a negative number, but in the financial world, this will always be positive. And this will cause our process to drift upward. And in the risk-neutral-minded sense, it will drift upward at the rate of interest. So the new component, the drift part, this part is the drift part, and this could be the random part or the stochastic part, whatever you want to call it. This ends up being, based on Ito's lemma, this ends up being the drift component, and then this component ends up being the new stochastic component. And I'll go over somewhat of a concrete example shortly, but what I'm basically saying here is this is the drift part, the drift rate, this whole component gets multiplied by dt, and the variance component, this was the square root of this, ended up being the term in front of the Ito's, in front of the Wiener process. And then if you just square both sides, you get the variance of it. And I'm just saying, no, we're not going to derive Ito's lemma here. That would be covered in stochastic calculus class, the derivation of it. Okay, so let's apply this to something a little bit more concrete. So we're basically saying we now have this interesting lemma, which basically says if you give me an Ito process, I can go and make up any formula that uses that Ito process as input, and the new thing that I've made up follows the Ito's lemma formula. So let's say our inputting process is a stock price, and the new thing is a forward price on that stock. So if you remember, a forward price, if you had a stock and you wanted to know what the forward price is, the formula would go like this. The forward price is equal to the stock price times interest. We would add interest to the price. So for example, if the stock price is currently $100 and the interest rate is 5% and time equals 1 year, what should those two people agree that the forward price should be 1 year from today? That would be $105. Right? We remember this from forward. So the forward price would be 105 as of today. Now, as time goes on, the forward price keeps changing, right? So we want to come up with a model for the forward price. We have a model for the stock price. We're using what we said before, the formula where the stock goes up at a normal interest rate and plus has variability to it. We'd like to come up with a model for the forward price. So we are interested in a forward price as time passes. Okay, so we'll let F be the forward price, S be the stock price. And at any point in time t, before the year ends or before the term ends, this formula would be true. The forward price should be whatever the current stock price is. And then also we would want to tack on interest from now, little t, until the end of the term of the contract. So this formula will tell you the current value of the forward. So as the stock price is jumping up and down, the forward price is moving differently, right? In fact, if the stock price was angling upward with the interest rate, the forward price would stay completely constant. If the stock price starts shooting up, the forward price will shoot up, but at with a different process to it. So does that, and like I say, maybe next week I'll go over an example of these two where we can graph the two together. But what I just want you to try to imagine is, as the stock price is moving around, the forward price is also moving around with it, but differently. And this function, so this would be like on our Ito's lemma, this would be our g function. We get to make up any function that takes an Ito process as input, and Ito's lemma becomes true about it. So, if we wanted to take this as our g, then based on Ito's lemma, this statement should be true. Everywhere you see a g here, change them to f for forward. Like I said, g is just any function we can make up that uses x as input. Now, f's, if you change the g's to f's and the x's to s's on that last formula, this statement about our forward price is true. This is the thing Ito proved. This will be true in all cases. So that's our F formula. So now we just go and calculate the, what do we need? We needed two first order derivatives and a second order derivative. We need the derivative of f with respect to x times a, we need the derivative of f with respect to t, and then we need the second derivative with respect to s. F's second derivative with respect to s. So we'll calculate those out separately. So based on this formula at the bottom of the screen, we calculate these three derivatives. So our first derivative of the forward price with respect to s ends up being this, based on the formula from the previous page. The second derivative of the forward price with respect to s with respect to s, there's no stock term here, so derivative of a constant is 0. And a lot of the easier examples in the textbook, the second derivative comes out 0. They get a much bit of a pain when this thing is not 0. And then the derivative of our forward price with respect to time ends up being this. So if we take these three terms and plug them into the Ito's lemma formula, we should get this. So I actually rewrote Ito's lemma and then plugged in this is the Ito's lemma in general, but I used F instead of G. I probably should have made those G's, just to say we're taking Ito's formula and then plugging it into our special case. But anyway, so what I'm saying is the calculation we came up with for the forward price, we said the forward price equals the stock price with the interest, the exponent being bt minus little t, tacking on that much interest. We came up with a new process. According to Ito's lemma, this statement is true. And hopefully this will help us somehow. But we're basically saying the rate at which the forward price changes is equal to the first derivative of the forward price with respect to the stock price times mu, which is the rate it increases, times the stock price. Plus, this is the first derivative of the forward with respect to time. That was the green component from the last slide. Then times 1/2 the second derivative of the forward price with respect to the stock price, which ended up being 0, times sigma s squared, this will get all zeroed out. Plus, this is the stochastic component, where we take the derivative of the forward with respect to the stock price, which ended up being this part, multiplying that by sigma times s times the Wiener process. So this whole thing is now a new Wiener process. This whole thing is now a new Ito process. It drifts upward at this rate, this times dt, and this component ends up being the standard deviation of the forward that maps to this stock price. And we can substitute f for everywhere we see s times e to the r t minus t, because we said those equal each other. So we can rewrite the previous equation. If we collapse everything together, we can rewrite the equation on the bottom in the different colors can actually be rewritten like this. So the rate at which the forward price changes, the forward price it derives its value from the underlying stock price. The forward price changes at a rate of mu minus r times the forward price times dt plus sigma, this is the sigma of the original stock price, and this is the mu of the original stock price. And this is the interest rate of the world around these two. And then we multiply this by the same Wiener process. So this gives us a formula for how much we expect the interest rate, this ends up being a formula we could use to model the forward, the corresponding forward to the stock price. So what would be the expected, what would be the, for a forward price, what would be the expected growth of it? Well, intuitively, before even looking at this equation, what would intuitively be the expected growth of a forward? The forward price originally, like in our original example, the stock price was 100 and the forward was set to 105. Now you let time start running. Would you expect it to go up from 105 or down from 105? What would be the expected change of it? So this component has, what is the expected value of this component? This is a Wiener process. This is a constant multiplying the Wiener process. A Wiener process starts off at 0 and is expected, it's a martingale process, it's expected to stay at 0, but it's expected to jump around. But it's expected to stay at 0. So if something that is expected to stay at 0, you multiply that by a constant, the whole thing is expected to stay at 0. The forward price, the stock price expected to grow at R. It was expected to go upward. The forward is expected to grow at whatever this is. This is the growth component. So this would be the price of the forward at any point in time, so that would be 105 and it could change. These two numbers would subtract, so this is the interest rate and then this is the mu, which is the expected growth rate of the stock. What would you expect those two, mu minus R, to be? So you wouldn't see it here, but what is the, forgetting about this Ito's lemma stuff, what would you expect a forward price to become over time? So like in our example where we had the stock price is 100 and the forward ends a year from now, so the forward price is 105. That's what the two people would agree to sell the stock for or buy the stock in 1 year. Would you expect that 105 to go up or down once you let time start running? Would it be expected to go up, down, stay the same? Well, like, if you signed a forward contract today with somebody, you say you're going to buy something from them for 105 1 year from today, and the thing's currently selling for 100. As time is going on, would you expect that the value of the thing to go up or down from 105? I mean, it might go up, it might go down, but would you have an expected change?
Expect it to go up.
Well, maybe I'm just not phrasing. Why would you expect it to go up?
Because you're trying to make money, right?
You expect the stock to go from 100 to 105, but the thing you agreed upon 1 year from today, would you expect that to change over time? Would stay the same?
Yeah.
Right, so the expected value of this component should be 0. In this particular case. So again, what we've basically done here is we've decided, and some people can argue this is something you shouldn't, this isn't perfectly correct. We decided to take stock and model it as an Ito process. Meaning, there's a component to it that grows up at the rate of interest, and there's another component to it that makes it variable. And we have the ability to put a constant in front of that variability to make it more volatile, if we want. If we allow ourselves to use that model for stock, then any function we dream up that involves that stock as input and time as input, anything we come up with, it could make no sense at all. You can come up with any function g, and Ito's lemma will be true about your function g. Now in this case we picked a function for g that was somewhat meaningful, the price of a forward for a stock. And then we cranked through Ito's lemma's formula, and then we decided that we came up with a formula to describe the new thing. And this would now model the forward's price. So instead of how is this useful? Instead of modeling the stock and then constantly calculating what would the forward's price be if the stock did that, we could just model the forward. So we now have a mechanism, this Ito's lemma, we now have a mechanism. If we have a process for some equity, we could model any derivative, anything that derives its value from that equity, using whatever function we want. And then Ito's lemma will make a statement about it, and if we clean up Ito's lemma, we might have a meaningful statement about it. So, oh, okay. So, is there any, I know that this is kind of a, it's an important topic, and just, it's kind of, now that we've seen an example, it might just make a little bit more sense. I wanted to go back, this is kind of the main Ito's lemma. It's a statement about not Riemann sum calculus, but stochastic calculus. Calculus when a Wiener process is involved. You can't use normal calculus. So the statement is, and it's a powerful statement, is this. If you have something, if you have a process that is modeled with a Wiener process and a normal mathematical function times time, put those two together, this is called an Ito process. And even theoretically, this part could be zero. So this part alone would be an Ito process. But we are allowed to have a stochastic part and a, what we'll call normal calculus component. You add these two together, and that is the model for some process. We now, with Ito's lemma, we have the luxury of dreaming up any function g, which takes as input x and t for time. And you have the complete freedom to make up any function you want. This statement will be true about the function you made up. Does that help us? Sometimes it does, sometimes it doesn't. Once we calculate all of these terms, we now have the new process. And the new process can tell it, might tell us something about the new process. We now have a way of modeling the new process.
I just have a question.
Yeah?
For the DZ part, how is that not normal calculus? Can you like
For which part?
the DZ part? Can you show us how that, like, that's not normal?
Yeah, the idea, why we couldn't just use, why this, this is a differential equation.
Yeah,
So
I know
here-
that. I know
right.
that the dxa with the dt part is a differential, but
And well, this is also a differential equation.
yeah.
But this component, so the question is, why couldn't we take this differential equation and use the stuff you learned in your differential equations class, your undergraduate class in differential equations, to solve it? Why would that not work? Why would those techniques not work? That's not really, that in your stochastic calculus course, they'll go over that. But the idea is that this component, this function, is not a smooth curve. That if you magnified it, if you looked at this curve and magnified it as much as you possibly could, it would still be jagged, whereas this would be a smooth curve. And so some of the rules of differential equations don't apply here. They apply pretty close, but they don't apply perfectly. And then the guy Ito gets credit for coming up with a way of solving this differential equation in terms of these partial derivatives. So actually, intuitively, this formula would not make sense if you used a standard solving for differential equations. You wouldn't come up with terms like this. But this goes on to be considered, this goes on to be true for this type of model. So now we've gone over one example where we take a stock price, and we said we used this formula to model a stock price, and then said I have another thing that uses stock as its input, and that would be the forward price. Applied Ito's lemma, figured out the first and second order derivatives, and then calculated Ito's lemma, and then made a new statement about the forward. Collapsed it all together and got down to a pretty simple formula, and now we have a process for the forward. So this ends up being useful in derivatives. So a derivative is anything that derives its value from something else. So the thing we're deriving our value from is an Ito process, then we come up with a new Ito process that describes the derivative product. And then that one can have a derivative and so on. So what might also be interesting is if we decided we're going to model stock with a formula like this, and then decided to come up with a derivative for a call option. If we said, I'd like to say, here's a model for stock, now I'll come up with a formula, instead of it being like in the forward case, instead of it being this formula, instead of this being our G, if we came up with like a C for call option, C equals some function of S, which will give us the current value of the call option, this new function C would become our G function. We use Ito's lemma, we come up with a statement about the call option. And then from the, we can then, from that formula, figure out what the expected value is. Right? That formula gives us a variance and an expected value. And the expected value is what we should pay for, the call option. So a real interesting use of Ito's lemma would be to, instead of trying to figure out the price of a forward with a forward, which is a derivative, deriving its value from a stock price, we'll try to figure out the price of a call option with a stock price, run that through Ito's lemma, and it'll give us a formula, and from that formula we can look right away what its expected value is. The expected value should be this one. The expected value, this part, the expected value of the stochastic part should always be zero. It's a martingale process. The expected value of this part should be whatever we expect the value to be. So if you wanted to price something, if you said how much money should I pay today for it, you could take the derivative product, run it through Ito's lemma, and this part is what you should pay for it today. This is the variability part that a risk-neutral minded person doesn't care about. They don't mind risk. As long as the expected value is zero, they're okay with risk. This would end up being the expected value. So if we took a call option on a stock price, ran it through Ito's lemma, came up with a new formula, this would be the value of it. So that would be an interesting thing to solve. Okay, any other question on this? Okay.